something about the walk plate. And you might need an access card, so I think I want to stick around people who have walk plates. All right, so we're going to.
Okay. First, thanks the organizer for the nice invitation to speak here in this nice workshop and in front of this nice audience. So today is a modular stabilization day. I will start with part 2, actually 2b, because I will talk about type 2b string theory compactification, while Lara is talking about about heterotic compactification. So why modular stabilization? So modular stabilization is a long-standing problem of string compactification and in particular string phenomenology. What is string phenomenology? String phenomenology is the branch of string theory that make contact between the string theory and the observed words. And the first problem that one has to face in this program is that string theory is naturally defined in 10D while we live in 4. So what to do? Then the standard solution is to take 6 of these 10 dimensions and wrap them on a compact manifold. Okay, so the first thing that one has to take in string phenomenology is a compact manifold. Let's say, for example, the most famous one for us, the Calabi-Yau, to have some supersymmetry at low energies. And okay, there is a cost to pay to pick up this manifold, and that is the manifold brings the moduli with himself, typically. Okay, and what are these moduli? Moduli are deformation, continuous deformation of the compact manifold, geometric continuous deformation, that keep the manifold a solution of the equation of motions. Okay, and why is it a problem? Is it a problem? It's a problem because in the 4-dimensional effective field theory, you would see this moduli as flat direction of the scalar potential. That is massless scalars. There is a bunch of massless scalars that we don't observe. Okay, so introducing just a compact manifold is not enough. One has to introduce new ingredients in the string compactification in order to generate a potential for this moduli and give them a mass. Okay, so you see how that is a crucial problem, and in fact modular stabilization has been studied in many corners of the landscape. I would say in any type of compactification string theory there have been attempts to stabilize the moduli. So I will review here type 2b string compactification. Lara will review heterotic compactifications. Of course, there are other corners of the landscape that we will not touch, but if you like, we can try to do this in the discussion session. So, type 2b. In type 2b, modular stabilization has been studied a lot in the last 10-15 years. And what are the appealing features of type 2b? So everything started with the flux, with the introduction of this ingredient that stabilized part of the geometric moduli of the Calabi-Yau. Now the nice thing about type 2b is that these flux have a mild back reaction to the geometry in the GKP version, in the sense that they just introduce a conformal factor in front of the Calabi-Yau metric, plus that it is actually the inverse of the Ward factor in front of the 4D. And also there are viable mechanisms to fix the Keller moduli, that are the remaining geometric moduli that at this level are flat direction, as we will see. And so we have the famous KKLT, large volume scenario, and there is also a possibility to stabilize some of them by introducing the D terms. So why is it important to talk about modular stabilization in a SUSY breaking workshop? Yeah, the fact is that SUSY breaking is a property of the minimum of the scalar potential. So what you should do if you want to study SUSY breaking is to stabilize all the moduli, go to the real minimum of the potential and see if their SUSY breaking, SUSY supersymmetry is broken or not, and then there you can see if it is broken, what are the generated F term or D terms, and what are the soft terms that these may generate. Okay, so let's start with type 2b. So as I said, the string theory is defined in 10D. So let's start from saying what is type 2b supergravity. That is the low energy theory of 10D string theory. So there are bosonic massless fields that and their fermionic part, and the bosonic one are the metric, and a two-form and a scalar, that is the dilaton in a Navier-Stokes sector. And then in the Ramon-Ramon sector, there is an axion C0, a two-form C2, and a four-form C4 that are organized in this 10D action. And this action, you see, this is written in a form that is as the famous SL2Z invariance, and you see that to write this manifestly, we have to write the axion, the dilaton instead with the axion into the axiodilaton, and this combination of the field strength of B2 and C2. Okay, so now we want to compactify this on a Calabi-Yau and maybe also introduce an orientifold involution. And this, as I said, produce a bunch of scalars. So in the closed string sector, we have the dilaton, that is a scalar, remains a scalar. Sometimes it's written as with this convention S, that is minus I tau. There are a bunch of geometric moduli that are called the complex structure moduli, and another geometric moduli that are called the Keller moduli. This is because the geometric moduli or the metric moduli of the Calabi-Yau threefold can be separated in these two sets, and because they can be associated to the deformation of the holomorphic tree form or on the complex structure of the manifold, as Calabi-Yau is a complex manifold, and to the deformation of the Keller form, as Calabi-Yau is a Keller manifold. So after you introduce also the orientifold involution, we have let's say the P form of your Calabi-Yau can be split in even and odd, and so this number, that is the 1-2 form that are odd under the orientifold involution, this number counts the number of complex structure moduli that survive the orientifold involution. H11 plus counts the Keller moduli that survive the orientifold involution, and H11 minus is the number counting these scalars here. Okay, so we have this master scalar, and we have to introduce new ingredients to stabilize them. Okay, so the first thing, I mean, the successful thing that was introduced almost 15 years ago, where was a background values for this field, B2 and C2, such that their field strength have a non-vanishing valve. Okay, so you have to do this by introducing this quantized values here for the fluxes. And you see that in the 10D Lagrange, when you compactify to 4D, you have this term here, and that depends on the internal metric, okay, by this, especially by this star here. So if you introduce a background value for G3, this will generate a potential, because here there are no derivatives of the matrix, a potential for the metric moduli. And in particular also will also generate a potential for the axiodilaton, because G3 has the axiodilaton inside. Now, from a 10-dimensional analysis, one can study, okay, the equation of motion. Now, see if some of the continuous deformation that before were there, and that preserved the fact that was a solution, are no more there. And one can see actually that from the equation, from the 10D perspective, one has a solution tells you that the three-form flux G3 must be imaginary self-dual. Okay, this condition can be translated into requiring that the 3-0 part and the 1-0 and 1-2 part of G3 is equal to 0. So since G3 is fixed because it's quantized, okay, it doesn't have a continuous deformation, this is a condition on the complex structure of the manifold. Okay, if you rotate the omega 3, so you deform the tree form, the holomorphic tree form, you will change the part of the tree form, the G3 that is 3-0, 1-2, 2-1, or 0-3. Okay, so this is actually a condition that can fix all the complex structure moduli and the axiodilaton. Okay, these are the other condition solution that you get, that was also reviewed yesterday, so I will not say more. Okay, but modular stabilization can be also studied from a four-dimensional point of view, and this is what we want to see. Now, as I said before, we want to have a 4D, we want to see that these moduli have been lifted by the generation of a scalar potential. So let's see this from the 4D n equals 1 effective theory point of view. Here, I mean, people worked out what is the Keller potential at 4D, and it's given by this form. This encodes here you see immediately the axiodilaton in the convention of S. Omega 3 encodes the complex structure moduli deformations, and here this is the volume of the Calabi-Yau that is written in form of the Keller form. Okay, the Keller form is just a linear combination with some coefficient Ti, and these are the Keller moduli. Now, the real Keller coordinates of true Keller coordinate of the modular space are this complexified thing in which appears not the Ti but this tau I, that basically are the volumes of the 4 cycles of the Calabi-Yau, and the C4 that is the 4 form of type 2b will generate a bunch of axions. And okay, but now the introduction of 3-form fluxes will now induce a 3-level superpotential, that is the famous Kukov-Van superpotential, that is of this form. So you see that depends on on G3 because this is what we introduced, and depends on omega 3. So it's in the right form to stabilize what we expect from 10D. So complex structure moduli and the axiodilaton. Okay, so one compute the n equals 1 4-dimensional supergravity potential by the usual formula, and one realized that actually because of a property of the Keller of the Keller potential for the Keller moduli, one has a no scale structure. Basically, part of these terms here cancel against -3 mod W square. In particular, the dependence here on the Keller moduli from this guy here disappear. You have only here as an overall factor. And so this potential is a positive definite, so it has a minimum at v equals 0, where at the minimum you have to set this dAw equal to 0. So you have, and this you can show that fixes the complex structure and the axiodilaton precisely in a way such that the G3 that you have introduced becomes of the right form, imaginary subdual. So at the minimum of this potential, you can work out what is the values for GS and also the VAV for this potential, and this will depend on the fluxes because these are the parameter of your equations. You solve the minimization equation and you get this thing. And moreover, at a minimum of the potentials, when the Vmin is equal to 0, then the Keller potential are completely flat direction. The Keller moduli are completely flat direction. Not only this, if the VAV of W, that we call W0 from now on, is different from 0, then the F term for the Keller moduli is different from 0. Okay, so this will be the derivative of W respect to the Keller moduli plus this term. The superpotential does not depend on the Keller moduli, and then you get this thing here. For W0 different from 0, this is typically different from 0. Okay, so at this level, for W0 different from 0, SUSY is broken. So, okay, now we have still some flat directions, so we need to introduce new ingredients to stabilize them. And okay, let's go to, yes?
What you say is that it is generic, the question.
Well, at this level, yes. If W0 is different from 0, yes.
Putting W0 equal to 0
is an extra constraint that can be not satisfied.
It doesn't make sense to talk about supersymmetry breaking if you're not at the minimum.
Well, for what we are going, I mean, yes, it makes sense now to talk about this. I mean, okay, it's there is a flat direction, and you see that in this flat direction the supersymmetry is broken along this flat direction. Okay. This is the only thing that I'm saying. Just a remark, because afterwards we need to remember.
Why you say that doesn't mean to speak about supersymmetry being broken? For the moment,
there's a limit where supersymmetry is restored.
Sorry?
There's a limit where supersymmetry is restored. It's the infinite volume limit. It's completely compressible.
But that's at infinite distance in field space.
Yeah.
Perhaps we can save we have this discussion set enough this afternoon as well. So. I want something for that.
No, just one.
Yeah, no, sure.
Okay, KKLT. It is Katsu, Carlos, Linda, and 3 ready. So, this starts with by assuming that the dilaton and complex structure moduli is stabilized at parametrically large scales. So then at lower energies, we are just left with this flat direction, and let's see what happens at these energies. So we have to look at a possible correction to the superpotential W. Now, because of shift symmetries of this Ramon scala C4, this prevents to have the Keller moduli that includes C4 in its definition as appearing in a perturbative way in the superpotential. And so we have to look at the non-perturbative effects. And actually, there are non-perturbative effects that can produce non-perturbative superpotential, and these are the famous A3 instantons. So these are D3 brane wrapping a 4-cycle in the compact manifold, or a Gaugino condensation on a stack of these 7 brane, for example, that realize a pure superreal Mills. Okay, the form of the potential will be of the superpotential will be of this form. That is an exponential of the Keller, the complexified Keller modulus, with a prefactor that will depend on the complex structure moduli. Okay, so let's consider the more simple example in this scenario. That is the one where we have only one modulus. Okay. W is of this form. We will have the W0 that at this level is a constant plus the non-perturbative effect. And then one can now compute what is dt W and see that now there is a solution equal to 0 if we satisfy this condition here. Okay, so now let's see what, so now we have to solve this with respect to tau, okay, to find the minimum. And immediately you see that because of this exponential, to have tau to be larger than 1, so to have a volume that is larger in string units, and to have then the supergravity approximation realized, then we need the W0 to be very small, okay, because of this exponential. So you see immediately that to be in the right region to trust the approximation that we are doing, we need W0 very, very small. Okay. Second thing to notice is that this will realize a anti-de Sitter minimum. This is a supersymmetric minimum with W different from 0. So this will be the value of the potential, and then we need to uplift, and we have seen yesterday what could be the problem for this. And in particular, I want to notice that now it will be, since now we have restored supersymmetry, the uplift will be actually the source of supersymmetry breaking. Okay, so some remarks about KKLT, and so here I said open issues. That's in my taste. This is why I don't like KKLT so much as today, basically. So first of all, we have assumed a separation of scales at the beginning. Okay, when we said assume that the complex structure and dilaton are stabilized large value, and then we see. But actually, what happens in KKLT is that there can be basically once you reconsider the minimum as embedded in the full moduli space, you see that moving in some direction, some tachyonic direction could be realized. Okay, and okay, this is a problem. And moreover, there is a delicate tuning of W0. W0 is something that depends on the fluxes. And okay, if you have a lot of fluxes, you can think that I mean, it's been shown that you can have a very, very small W0 due to some intricate cancellations. Okay, but it is not a typical value of W0. So if you have few complex structure modules, so if you have few fluxes, then it can be that W0 you cannot take so small, and then all this minimum is not there. I mean, not in the region where you trust the approximation. Now we'll see that also there's a problem in neglecting some perturbative corrections. Here we are just considering non-perturbative correction to W, and also the last. I mean, to stabilize the module in this way, if you have many Keller moduli, you need many non-perturbative effects that produce a non-zero non-perturbative superpotential. And this can be a problem, especially once you try to combine modular stabilization with model building. Okay, so let's see. Let's try to see to introduce. I mean, also other possible corrections in a consistent way. Okay, so there is non-perturbative correction to W, but we can also add some perturbative corrections. So we have the corrections are there. One has to consider also them and see what happens. There will be also non-perturbative correction to the Keller potential that we will not consider here because they are very subleading in all what we are saying. So once you insert this K and W in the scalar potential, you will get, roughly speaking, a sum of this. So you have a term that is the three-level potential, a term that is generated by the perturbative correction of K, and one of the perturbation of W. And in this no-scalar model, we have 0 for the three-level potential, and the magnitude of the other terms are of this form. Now, these terms are important exactly because this is equal to 0. Okay? If this was not equal to 0, then we could stabilize the module at 3-level, and then this correction will just shift a bit the minimum. Now let's see KKLT. So take W0 much smaller than 1, and W0 of the order of the non-perturbative effects in such a way to have the possibility to have dt equal to 0. And then you see that in this regime here, if you plug this in here, you have that the contribution of the perturbative effect of K on the potential is actually suppressed with respect to the superpotential. Okay, so in this limit, actually, the KKLT can be present, KKLT minimum. Okay, you can also see that since this perturbative correction will go, as we will see, as inverse power of the volume, while the non-perturbative effect will be some exponential with some constant here in front. To have realized this suppression here, you cannot have a very large volume. Otherwise, this term will be completely suppressed, and with respect to this. Okay, so this shows you that in KKLT it's also difficult to have a very large volume. Okay, so we see that for generic value W0 we need to include also the perturbative correction of the Keller potential. So what are these corrections? So in type 2b, the leading one is an alpha prime correction coming from an alpha prime cube correction coming from hardware 4. This is encoded in the Keller potential. Okay, in this way. So basically, it goes to correct the Keller potential of the Keller moduli by shifting the volume by this term here. This term depends on many things, in particular on the Euler characteristic of the Calabi-Yau threefold and on the axial dilaton. This term comes because this volume is in the Einstein frame. Okay, after rescaling, everything disappears. Okay, so let's consider now this Keller potential. Let's also take the usual non-perturbative superpotential. The non-perturbative effects are still there. And now let's see what happens. Okay, so again, V0 is equal to 0, and this will stabilize the complex structure and the dilaton by the usual equation. And for generic value W0, there is, as we've seen, there is no regime in which this is realized, and so KKLT is present. Okay, so now we have introduced alpha prime corrections, so we must. And we have introduced only the first one. Okay, so we must be careful that the other corrections don't enter into the game, and to have a separation between the leading and the subleading corrections, we have to ensure now that the volume is large. Okay. Okay, so So now what's the strategy, let's say, to stabilize the moduli? So we have a potential that is of this form. Now this is the first time that appears. This is the D-term potential that in type 2b can depend on the Keller moduli. So we have this potential here. We assume now that let's say that the volume is very large. So we just look at the region in the module space where the volume is large. We do the minimization, and at the end we have to check that the point that we have found is exactly in this region. Otherwise, we cannot trust the approximation that we are doing. And in this 1 over the volume expansion, the D-term potential coming from fluxes on the 7 branes and depends on the Keller moduli. This is of order 1 over the volume square. It is the same order of the 3-level F-term potential coming from the Gukov-Alpha-Witten superpotential. Okay, so these are the leading term. These are positive definite. And then a subleading order, so order 1 over the volume cube, we have a perturbative potential that can be generated by either the alpha prime that we have seen, or some GS correction that we are not going to talk here, because they are even subleading with respect to the alpha prime. And also we have a non-perturbative superpotential that generates also a term of order 1 over the volume cube. And the strategy is to stabilize the moduli order by order at a large volume expansion. Okay, so at first the first terms, as I said, are positive definite. So they will, if there exist points where these are equal to 0, this is the minimum, and this will stabilize the complex structure dilaton and some of the Keller moduli, some combination of the Keller moduli. And then as subleading order, we have the remaining Keller potential, Keller moduli fixed by the usual, by the perturbative, non-perturbative correction. Okay, so let's take an example. That's a famous example for large volume scenario that is coming. So we take what is this? Is P41169. So it's an hypersurface in this projective space. Now this projective space is singular, so you resolve this space by going to the historic Hamming variety, and here you have so in this historic variety where these are the coordinates of this complex space, and these are the identification, basically the weight of the identification of these coordinates, the scaling. The hypersurface equation will have these degrees. Okay, so this is what this means. You can study what are the topological numbers of this Calabi-Yau. You see that it has 2 Keller moduli and many complex structure moduli. So you can choose a basis for the second homology class. So a basis of 1-1 form. That can be written in terms of the Poincare dual divisors in this way. So we can choose just the divisor where this coordinate vanishes and the divisor where this coordinate vanishes. And now you can write down the volume of these divisors and the volume of the Calabi-Yau in terms of this tau. Okay, and you see that it has this very simple form. That is the most famous Swiss cheese Calabi-Yau. Okay, so you have a 4 cycle that is giving basically the volume, and this tau is giving the volume Calabi-Yau. This tau is giving the size of the holes. Okay, that you have to subtract from the Calabi-Yau. Now it turns out that this divisor here is rigid, and it has the right properties, the zero-mode structure, to have the non-perturbative effects realized here. So actually also this other divisor can support some non-perturbative effects, but as we are going to take the limit where the volume is large, we will take the limit where tau b is much bigger than tau s, and then this a contribution like this with the s b instead of s will be suppressed. Okay, so this is so you plug in this the volume, the explicit volume form inside the Keller potential, the Keller potential and superpotential inside the scalar potential, and you get this form with these 3 terms. And then you look for minima. Okay, so you don't look for supersymmetry minima, you just look for minima of this potential. So first of all, just notice that when if you take tau big, so the volume very large, and this relation satisfied, what happens to the potential is that is going to 0 from below. Okay, while at very small tau b, this is bigger from 0. Okay, so we expect this to have a minimum, and actually a minimum at a large volume. And in fact, you minimize this, and you expect to the two coordinates that you have, and you find these relations. Okay, tau s is 1 over gs, more or less, proportional to this. And in particular, the volume here has an exponential relation with respect to this Keller modulus tau s. Okay, so this means that since tau s we want it to be larger than string units, and also because of this relation gs, we will look for vacuum where gs is small, so this will be bigger than 1, then we'll see that the volume is immediately very large, exponentially large. Okay, what is this minimum? This minimum is anti de Sitter. Okay, with now it's the potential at the minimum goes like 1 over the volume cube, and there are no tachyons here once you also consider the complex structure and the dilaton directions, because every time you move in that direction, that you remember the potential is positive definite with respect to dilaton, to the complex structure dilaton directions, so you will add terms of order 1 over the volume square, positive term of 1 over the volume square. Okay, so every time you move in that direction, and this cannot compete with the order 1 over the volume cube, and this allows you to show that this minimum is protected by tachyonic directions. So one can also try to see what are the scales of this, and see also if the effective field theory approximation that we are using is satisfied. One can compute and you see that in all these scales, all these masses, the volume appears. And the fact that the volume is very large gives an hierarchy between these scales. Okay, so we have the string scale is the biggest one, even though it's suppressed with respect to the Planck scale. The Kaluza-Klein comes after, and then you have the mass for the complex structure and the Keller moduli and the gravitino. And so first of all, we notice that okay, since the volume is large, we satisfy the condition to have that we want to trust the alpha prime expansion. So the volume string frame is bigger than 1, much bigger than 1. And also we have that the gravitino mass and the mass of the moduli are all smaller, much smaller than the string and the Kaluza-Klein scales. Okay, so actually we are taking a 4D effective theory. We are discarding the string scale, the string states, and the Kaluza-Klein states. M pi is MP is the 4-dimensional Planck scale.
Okay.
Okay, so this kind of minimum where the volume is exponentially large is this is what is called the large volume scenario. Okay, because we get large volume. Okay, but large, very large. No, but it's naturally large. Okay, so you don't have. So then. We have said this minimum is anti de Sitter, and then we need the Sitter. Okay, so we need to lift. Now here there are many ways in which it has been realized, also quite explicitly. And okay, maybe this will be. Tomorrow is the Sitter, so just here I mentioned this thing. So you have a possibility to lift it by some d terms that is cancelled, but induce some f term that has a positive contribution, and then this will lift. Or you have an f term from a dilaton dependent non-perturbative effect that gives also a positive contribution. Or you have this Keller uplifting, which you just consider the potential that we have seen before, but for some range of the parameters, this already gives you a de Sitter minimum. Now I want to stress that in all these cases, it's not that you find the large volume minimum and then you add a term that is positive to lift it. You add a correction to the potential, so a new ingredient that actually generates this new term. You reconsider the potential, you find the minimum, and the minimum is de Sitter. Okay, so it's a de Sitter found at the level of the effective field theory, of the 4D effective field theory. Okay, now SUSY breaking. Since,
You are saying that the potential plus the uplift term is supersymmetric, I mean, it is the potential of a supersymmetric theory.
yes, of a 4D n equals 1 supersymmetric theory, supergravity. Okay, SUSY breaking. SUSY breaking is given by the the supersymmetry breaking is given by the fact that we have f terms that are different from 0, and in our case are the Keller moduli that break supersymmetry. Okay, so we have the f term is this. Now remember before when I said that in GKP supersymmetry is generically broken. Okay, we didn't have this term. We had just this term, and now this term that is different from 0 and breaks supersymmetry is actually still the leading term in the large volume scenario. Okay. So supersymmetry, that's why I wanted to stress. So now you have generated a minimum, but the supersymmetry breaking is still given by the GKP supersymmetry breaking scale. And this is just a correction to that. Okay, so now usually you take this definition of SUSYs, of the supersymmetry breaking scales, and then this sets the vacuum energy and the boson-Fermi mass split. Okay, but this does not happen in large volume scenario because at leading order, this theory here is a no-scale model. Okay, so you have that this term here is actually cancelled against this at leading order. So the vacuum energy is actually 0 at the leading order. So you don't, and also the bosons that break supersymmetry in this case are the Keller moduli, and these are massless, flat directions at leading order. Okay, and actually what sets the boson-Fermi mass split is now is the gravitino, and the gravitino as this form is suppressed with respect to 1 over the volume with respect to the Planck mass, and is also smaller than SUSY. Okay, so now we have to mediate the SUSY breaking to the visible sector. And okay, since we have a supergravity theory, we should do with the usual procedure. So we expand the W and K with respect to the matter fields, and this will generate some masses, and these masses will depend on the Fi term of the moduli. And if these are different from 0, then the soft terms are generated. Okay, so since I'm running, I will be quick here. So basically, this is the expansion. We have also to consider the gauge kinetic function. This depends on the Keller moduli and also on the dilaton. And of course, to derive the soft terms, the important thing is to have the matter Keller metric for the matter fields. That is this coupling here, and this is unknown. So, but the nice thing is that what you can say is something about its dependence on the volume, okay, by looking at the physical Yukawa coupling, and this has this scaling with the volume. Okay, so let's go to a nice situation in which actually the F term for the volume for the F term for the Keller modulus relative to the visible sector. What I mean that we have roughly speaking a brane wrapping this force cycle, okay, and this force cycle then is what I call the visible sector force cycle. Now in case we are in a situation with the brane singularity, which this force cycle shrunk, this F term is actually 0, okay, and actually the visible gauge kinetic function is proportional to S. And this is the situation in which we have what is called sequestering. And you can see this from the gaugino mass. The gaugino mass you can compute as with the procedure that I outlined before, and you see that this is actually suppressed with respect to the gravitino mass with 1 over the volume. So it's a big suppression. It's much smaller than 3/2. This would not appear. It would not happen if this will not be 0. You will have this of order of m3/2 may be suppressed by a logarithm of the volume factor. Now one could wonder, okay, but then if we have this sequester, then I have anomaly mediation that contributes more. No, because here we are in no-scale models. Again, there is again a cancellation between the leading terms, and what we have is that the contribution to the gauge genome mass from anomaly mediation is suppressed by this factor with respect to this one. Okay, so in the last 5 minutes, I want to advertise a bit what was the progress in the last years, and so far we have just talked about moduli stabilization. We didn't consider any visible sector. Just assume that you can put one, but I mean, in the last year there have been a lot of progress in model building in type 2b. Especially, and with the 7 brains, also the 3 brain at singularity. So, I mean, this was the right moment to start to combine the two approaches, so to construct models that realize both modular stabilization in a quite explicit way, and to have explicitly your construction of your visible sector or hidden sector or all the method that you need. Now, this thing has been, I mean, this hope and this program has been started time ago, because I mean, this is what you should aim to at the end in string feno, and that some problems has been found in doing this. So the first one is that there is a tension between the Keller modular stabilization and the introduction of perturbative effects. Basically, if you want between the introduction of non-perturbative effects to stabilize the moduli and the fact that you want chiral states in your spectrum. Okay, and the problem is that to generate a chiral spectrum when you have these 7 brains, you need to switch on some gauge flux on the brain, and this can also induce if the divisor wrapped by the brains is intersecting the non-perturbative divisor. This can generate extra zero modes that could kill the non-perturbative effects. And this actually, basically, effectively what happens is that the prefactor of this non-perturbative effect will depend on some matter field, but the matter field we want to have zero VEV, because we don't want this will be charged under the standard model gauge group, so we won't want them to be different from 0. And that this would mean that this would be equal to 0, because when this happens, also AI is equal to 0. And so you would like to have a non-perturbative superpotential generated on some divisor, but it's not there, and then the potential is not generated. So you have to take care to be careful where you put your visible sector, and if this visible sector intersects the non-perturbative effect that you would like to survive, then you have to constrain the flux that you switch on that. So the best place where to put a non-perturbative effect is at the Pezzo surface, because these surfaces intersect. I mean, it's a shrinkable surface, and the intersection with the other divisors is quite constrained. So it's more easy to find divisors in your space that do not intersect geometrically this non-perturbative effect. Okay, other problems comes. Okay, this is the mildest problem. How much time do I have? 5 minutes. Okay.
Take your time.
Okay, so this is the mildest problem. Basically, if the brain wraps a non-spin divisor, then the quantization of the flux is forced to have a gauge flux different from 0. Now, for non-perturbative effects to contribute, sometimes you have to require that this curly f is equal to 0. And this you can do, for example, by a proper choice of the B field if f is different from 0. And but you cannot do this game with all the non-perturbative effects that you have in your, because the B field is you choose once, and then okay. So well, you choose the B field to cancel F for one non-perturbative effect, but maybe on another cycle this curly F is different from 0. Now, I said this is the mildest one because actually it's not always true that the curly F must be equal to 0. This is better to be like that for the Gaugino condensation, because you don't want extra matter that can spoil the Gaugino condensation. But for the instantons, there is also the possibility, as was studied by Iñaki and Per in a recent nice short paper. You have the possibility to have, let's say, a rank 2 instanton, roughly speaking, that can survive also with an F different from 0. No, it's not clear, but it's better to have a pure superniamis. Right? So these were just okay. In very specific model, you can overcome these problems, and but for a generic statement, or for a search, it's better to have. Okay, as I was saying, that with this rank 2, you actually can have the thing that for phenomenology, this rank 2 maybe it's less appealing because already the 3 instanton are disfavored with respect to the Gaugino condensation, because they basically they have this A here that is bigger, the E3 instant with respect to the Gaugino condensation, and then this will produce a much larger volume in the large volume scenario, and this would suppress a lot the scales and maybe going too low that we don't observe. The last thing is this fact. I mean, the fluxes on the brain generate Fi terms, and this enters in the D term, and minimizing the D. Yes.
So the distinction between rank 1 and rank 2, that's a large volume notion. But for instance, you typically want the volume to be small enough. So if it's really small, you still have enough prime corrections, that notion is no longer there. So there's no parametric suppression anymore. The rank of instant.
Yeah, okay, but if you want to wrap this on a large cycle, so you want an instant. Yeah.
If you are large volume, that's.
Yeah. But the fact is that since we want to do this large volume scenario, then these are the instantons that we. Nice. Okay, so okay, now I have 5 minutes. Okay, so what happens at the leading order in the D term minimization? I remind you that is one of the leading term in the potential, and we have to, and it's a positive definite, so basically must be equal to 0. Well, in general, it will stabilize some combination of the Keller moduli, but in particular, if this divisor is a del pezzo, what this minimization implies is actually that this divisor shrink. Okay, so you see that the volume of the divisor is stabilized to be 0. And so if you want to avoid the visible sector so if you don't want to consider the 3 brain at singularity, it's better to avoid a visible sector on a del pezzo divisor. Okay, so what's the strategy then if you want to stabilize the Keller moduli and avoid this problem? Well, we consider a set of examples in which we were able to proceed this way, and basically what you do what I said along this talk. So you stabilize the moduli order by order in 1 over the volume. So first you have the minimization that will fix some combination of the Keller moduli. Maybe it will fix the cycle to shrunk, and it's good if you want to have the brain singularities, or it fix some combination of them. So then at lower energy you have less Keller moduli left, and maybe you have just 2 left, and this then it's enough to have one non-perturbative effect that survives in your construction, and together with the alpha prime correction, this will give you generically the large volume minimum. And if there are some Keller moduli that are still flat direction, and then you need to consider the subleading correction that are AGS. Okay. And okay, I just mentioned at the end you have to check that your what you find, so the numbers that you find for your Keller moduli, are inside the Keller the Keller cone, and also satisfy the large volume. You want at the end, you have used the large volume approximation until the end, and then you want to check that. So what we did was to consider Calabi-Yau with H11 equals 4 and 5, and study different setup with brain with visible sector on intersecting brains or a brain at singularity. Okay, so I will here I wanted to show you an example, but I don't have time, so I will just very briefly go through it. So this is just an example of a toric ambient variety where you can take an hypersurface, and this is a Calabi-Yau. You can compute what the number, the topological number, the intersection form. This will allow you to compute the volume, and also to see what brain setup you can put in it. So in particular, in this example, you will have two del Pezzo divisor that, if are shrunk, can support the three brain singularities. These are exchanged by the orientiform involution, so the physical sector is just one D brain singularity. The singularity was actually C3 mod Z3. We had you can also see where the plane are, and these actually were not touching the singularity. And so the visible sector in this case was realized by a trinification model. You can study the hidden group that has these two sectors and see that actually one can have one can have actually a gaugino condensation on one of these groups, and stabilize the moduli order by order in 1 over the volume, and see that actually one gets a large volume minimum. And also here we are able to consider a way to lift to the sitter. So actually we found the sitter minimum, and also we study SUSY breaking and see that here we have realized the sequestering scenario in which the gaugino mass is of order 110 TeV with the volume of this size. Okay, conclusions. So we have seen that in type 2b we can have all geometric moduli stabilized by several ingredients, and what you can do is to assume a start point to have an overall volume that is large enough to trust the 1 over the volume expansion, and then order by order you stabilize all the moduli. And as you have stabilized all the moduli, one can study SUSY breaking subterms. One also realizes the sitter. And at the end, one verifies actually that the volume is large. Now, open problems, because this thing is not ended. First of all, it would be nice to have an explicit complex structure moduli stabilization. Here we have just said, okay, the complex structure will be stabilized. Generically, they will be, but if you know the exact value of the stabilized point, then you can compute what is GS and W0 that are realized at this minimum. We have done this in a paper in which we used the trick, and we switching on very few fluxes. You can actually be able to stabilize many complex structure moduli in a controlled way, but of course at the end we want to have many fluxes. Okay, another open problem is the prefactor that is very difficult to compute. Is another non-explicit thing in W. An open problem is the open string moduli. Okay, these are still difficult to stabilize, and that's also a reason why to go to lift to these models to have theory, to have more control over this module. Thank you.
Okay, I think the questions will move to the discussion. So the next speaker should maybe get ready. You have the. Oh, it's over there. Okay, so. So our second speaker this morning is Laura, who will talk about heterotic.
Okay. So first I just want to say thank you to the organizers for an excellent workshop so far, and thank you to Roberto for giving me an excellent lead into all the stuff I wanted to say, because let me go forward here. As I want to talk about in some detail today, moduli stabilization in heterotic theories is considerably younger than it is in type 2 theories. The tools are less well developed, and I'm not going to be able to get quite as far to the final punchline as Roberto did. But I do want to sort of outline a set of tools and how you could conceivably put these together and where some recent progress has been. So a few points to take away before we get started. One of the main differences to type 2 theories in heterotic compactifications is the fact that compared to type 2 theories, the process is somewhat more constrained. And this is primarily because of the fact that there is no real separation in the theory. There's no notion of a local heterotic model, no separation between the gauge and gravitational sectors, in the sense that your gauge fields in heterotic are spread over an entire compactification space. So really, in order to address the question of moduli stabilization and supersymmetry breaking, this has to happen in conjunction with model building, all at relatively the same time. So you really want to put three things together at once. Also, compared to type 2 theories, in which you can have sort of a tinker-toy approach of putting things together, you can do model building on one stack of d-branes and moduli stabilization, the supersymmetry breaking in other places. There's not a lot of room in an E8 cross E8 heterotic theory. There's really only one hidden sector. For example, if you want to build a standard model in one E8, you really only have one other place to put tricks. Limited ingredients in terms of the types of fluxes, specifically Nouveau-Schwarz fluxes and 5-branes. And then your non-perturbative effects, roughly the same as in type 2, worldsheet instantons and gaugino condensation. Also, again, because of the structure of the theory, things like gauge-mediated supersymmetry breaking are not really available to you. So if you're going to break supersymmetry, it's probably going to be gravity-mediated if, for example, you put it in a hidden sector. So this is just a set of things to bear in mind for the approach. So really the tactic I'm going to take, rather than giving you one complete model at the end of the day, is going to be to give you a collection of tools that contribute to this potential that you need to minimize. You need to put it all together and see what you can do. So I'll try and set that up, and then we'll see how far we get. Also, apologies in advance. Because of the limited time in this talk, I'm only going to discuss smooth large volume, well, I said Calabi-Yau here, I'm going to talk a little bit about non-Calabi-Yau, but smooth large volume heterotic compactifications. There are many interesting things in orbifold models, free fermionic models, rational CFTs, duality arguments, etc., that I won't be covering. So this is not comprehensive heterotic, but just a quick cross-section of one area. So the 10D heterotic theory, I think most people are familiar with. We're going to begin in 10 dimensions. The main ingredients that we have to play with are a metric and a three-form three-form flux in 10 dimensions, field strength. We also have gauge fields that live in either E8 cross E8 or SO32. I'm going to be focusing on the E8 cross E8 case for more interest for phenomenology. We have these fields in 10 dimensions, sweeping out our sort of standard Yang-Mills and supergravity multiplets. And of course, we're doing an expansion in alpha prime. We're going to be working to leading order in alpha prime for the most part. We have an n=1 supersymmetric theory in 10 dimensions. We're going to be concerned with reducing supersymmetric theories down to 4 dimensions. Of course, we want to break supersymmetry, but we want to do that in a controllable way. So we hope to begin with a supersymmetric theory and spontaneously break supersymmetry in vacuum. To that end, we have a set of supersymmetry constraints that we have to satisfy in any dimensional reduction. And also, importantly, anomaly cancellation conditions. The various ingredients of our theory, the curvature, the gauge bundle field strength, and the three-form field strength all have to talk to each other and satisfy non-trivial Bianchi identities. So one solution that we're familiar with and that I'm going to spend most of my time talking about will be a 4D n=1 solution where we get a 4-dimensional maximally symmetric Minkowski space, for example, with h=0 and the dilaton equals constant. And this, of course, is the familiar Calabi-Yau solution. In this case, the gauge fields in my problem have to satisfy a set of partial differential equations known as the Hermitian Yang-Mills equations, and we'll come back to that. So this is going to be the solution that we'll look at in the most detail, but before we do that, So I should say, before we, I'm going to set this up and talk about some of the issues. I will talk about things where we do not consider Calabi-Yau compactifications, but just different geometry from the beginning. But this is where we're going to spend most of our time. So in a background like this, as Roberto very nicely set up, we have moduli that preserve our equations of motion. Most of these are the same as in the type 2 setup, the dilaton, Kähler, and complex structure moduli, the geometric moduli of the Calabi-Yau background. And in this case, we're also going to have vector bundle moduli that come from degrees of freedom in the connection, which satisfy these differential equations. So these are gauge bundle moduli. The question is going to be how to stabilize these moduli. And in general, you would like to take an approach much like in KKLT or large volume. You want to do this sort of a step at a time, attacking different layers of these moduli, hopefully in controllable ways with separation of scales or whatever else you have at your disposal. So one possibility, and the most obvious one, is you have a very beautiful and well-developed toolkit in type 2 compactifications. Can you just import much of the same technology into the heterotic context? So the first pass is something like KKLT. Some of the most problematic moduli, the dilaton and the complex structure, like this guy and these ones, we've heard about adding flux, as Roberto talked about, and hoping that you have some sort of controlled back reaction so you can keep the Calabi-Yau compactification to some order and watch these moduli be stabilized. The problem, as I'm going to discuss in detail for a second, is that you have only one type of flux in heterotic. So you could try doing exactly as Roberto set up. You could introduce flux in background. You could consider, in the four-dimensional theory, this would appear as a moduli lifting through something like a Gukov-Vafa-Witten superpotential, which you can expand, as in special geometry, in a basis where these are complex structure moduli and a prepotential. You will have some sort of harmonic quantized flux. Here, omega is the holomorphic 3-knot form of the Calabi-Yau background. And you can just look at your potential you want to minimize and say, can I find some minima with pure flux in a heterotic background, the same as I did in Roberto's talk. The main differences to type 2b, however, superpotential does not depend on the dilaton, and most crucially, unfortunately, the beautiful numerology that we saw in type 2 with no scale structure does not happen in heterotic. We end up with 4 instead of 3 in the crucial place, and so naively, dilaton and Kähler moduli are runaway. We're not going to be able to ignore vacuum values of W as we did before. So let's just play with a scenario and see what we would have wanted to have happen and what the problem is. So imagine, just very simply, that you want to try stabilizing moduli by having a background flux superpotential due to this Nova-Schwarz flux, and you want to, say, combine something non-perturbative like gaugino condensation in order to stabilize the dilaton. I should mention that this prospect was noticed very early on by guys like these when they first were talking about gaugino condensation. And there were actually some attractive features of this scenario back in the day. So they noticed that in heterotic I have 2 E8s. Imagine that I did all my interesting model building in one of the E8s and leave the other one empty. If I leave the other E8 empty, it can naturally condense, and you can ask, after an E8 condenses and gets gravitationally mediated back to the visible sector, what scale of supersymmetry breaking would you have if you could minimize a potential like this? And they realized this was almost exactly a TeV scale. Naturally, it was very beautiful. The only catch is that you have to find a minima. And this is, of course, the problem. So non-perturbative effects at weak coupling, you want these to be small. Very schematically, you need a flux superpotential to also be small at minima. And the question is, can you do this? So as Roberto mentioned, in general, if you either need something like no scale structure or some sort of tuning in order to pull this off. So you can just ask, can I do it? In order to do that, you need to know explicitly this prepotential in some examples. So one example where you know it very well is the large complex structure limit, worked out by Candelas Font et al. In the 90s. Here you can actually just do this minimization, and you can see intuitively where the problem is, which I should say these guys knew as well at the time. The problem is that you have integer quantized flux, and in general, after you work out what the minimization looks like, schematically you're trying to balance something exponentially suppressed against something integer quantized, and it doesn't work. So you can manifestly prove that this doesn't work in the large complex structure limit. You can also try to just find minima, play tricks in various geometries, any place where you know the prepotential. You can scan over all possible flux integers using your one real flux, the Nova-Schwarz free-form flux, and try to minimize numerically. I should have had a citation here. Systematic searches by Gray and Lucas, for example, have been done. They've done some of the most thorough stuff on this that I've seen, and they thus far have not found any flux vacua where this simple trick works. This is not a no-go theorem in heterotic, but it's clearly a lot harder than it was going to be in type 2. So you need some sort of alternative approach. You need a different set of tools to try and stabilize moduli if you're going to stick to Calabi-Yau compactifications, or you have to give up on Calabi-Yau geometry to start with. So let me just have one slide on just a list of where we might want to go with this. Other options, if you consider just heterotic backgrounds, you can consider alternatives to the Calabi-Yau background, where we have a maximally symmetric space with H0 and the dilettone constant. One of the simplest and most natural is to say, let's still keep Minkowski space, but have a non-trivial H at 0th order, and a phi that will vary over that space. This is the familiar Strominger system. In all these cases, you can quantify your deviation away from the Calabi-Yau background by these torsion classes, for which you can write down a 3 form and a 2 form. This is essentially a deviation from the holomorphic 3-0 form and the Kähler form of your manifold. You can parameterize how you're deforming away from Kähler in a form of this type, or how you are not Kähler in a form of this type. So Calabi-Yau and Strominger give you Minkowski space in 4 dimensions. You could also try more exotic solutions like half-flat or generalized half-flat solutions, where you have torsion classes. These lead to domain walls in 4 dimensions and more general torsional geometry. In general, these will have much less moduli. Perhaps interesting things can be played with. Some recent progress has been made in this area, particularly recent work by Andre Lucas looking at moduli stabilization in the half-flat and generalized half-flat case. And generalizations of this, which I couldn't fit on this slide, very generalized half-flat constructions due to Gray, Larforce, and Lust. So this is an exciting area to consider. Just let's consider more general heterotic compactifications, forget about Calabi-Yau. The problem for where I really want to go for string phenomenology is that the geometry in these cases and effective field theory is still poorly understood, particularly spectra and things like this. So the states of the theory and model building. So this is very exciting. If I have time at the end, I'll talk about some nice new results from more general non-Calabi-Yau backgrounds. But for now, I want to still stick to Calabi-Yau and see what other tools I have available to me if I can't just use flux, KKLT, etc., the way that I'd like to.
Why is this emphasized in heterotic? Was opposed to type 2b?
You could ask exactly, you could talk about SU3 structure compactifications in type 2, and as of course you know, there's lovely stuff that's been done on that.
My question is, if you're introducing fluxes, when you say these deform the geometry away from Calabi-Yau, but these fluxes are there to cancel in the potential, the energy density of a non-perturbative effect. You want to introduce them to cancel against e to the minus t.
In the case that I was interested in, yes, because I can't stabilize the dilaton purely with flux, I might say, can I balance flux and gauging condensate?
So the energy density associated to these things that deform you away from Calabi-Yau is set by the scale of the non-perturbative effect.
In one case. So what I'm emphasizing here is actually not a deformation away from Calabi-Yau. I'm talking about forget Calabi-Yau entirely and just do a different compactification of the theory. So
there'll be a bunch
separate.
of integers that go with this domain wall variation, and I think what you're getting at is you'd have to find some way of having enough control to tune that to be very small so you could balance it just like you did in KKLT, and that's obviously incredibly hard. But
And also just to say, I wasn't considering just Calabi-Yau deformations here. These could just be completely wildly new geometries, and you could say, could I do anything interesting for pheno? As James points out, you have to deal with these domain walls, and the pheno of that is going to be problematic. But I'm sorry. Maybe I didn't
my point is this: so you introduce non-Calabi-Yau fluxes, if you like. That you introduce some fluxes.
Actually, can we postpone that to the discussion? Because
so no questions are allowed in the
no, I think we should actually have the talks, and then we can remember the question.
I'm sorry, that sounded like a good question. So let's definitely come back to it. But just to answer what I thought you were saying, I'm just flashing up that I didn't have to consider Calabi-Yau.
I wanted to say, so don't answer.
Okay, apologies. Sorry about that. We'll come back to it. Okay. So the point of this slide, independent of what was asked, is just you could consider things that are very different from Calabi-Yau backgrounds to start. That could be a very interesting thing to do, and there's some cool tools available to you. And in general, much less moduli. So if you care about moduli stabilization, maybe you wanted to forget Calabi-Yau in the first place. Unfortunately, you don't have a very good toolkit to address it. So we're going to come back to this if I have time, but for right now, we're going to stick to where we actually understand how to really work out the effective theory. And the argument that I wanted to say in terms of a naive KKLT approach is that this is very hard in heterotic simply because you have a different structure than in type 2. So it would be nice to have some different tools. So I want to now catalog what some of those tools might be. So the big ingredient that you have in heterotic that you don't have in type 2b, or at least in quite the same way, is you have some very serious constraints that arise because of the gauge bundle in the E8 cross E8 heterotic compactification. So I want to look in detail at supersymmetry conditions in the gauge fields and how they interact. So I mentioned that in a Calabi-Yau vacuum, you have equations of motion which non-trivially constrain the way that the metric of the Calabi-Yau, and as we'll see in a second, the complex structure, interact with the gauge fields. The solution to these equations in general depends on all the moduli in the problem. So it depends on complex structure, Kähler, and bundle moduli. And a very simple mathematical fact is that some regions of moduli space will provide a solution and some not. So if you're astute at this point, you might say, why am I talking about a, quote, moduli space if it doesn't satisfy my equations of motion? And indeed, this is a very good question. So one of the bits of progress in the last number of years has actually been more about moduli identification in heterotic theories than stabilization. So can you really work out, not just thinking in a type 2 language at 0th order Calabi-Yau plus gauge fields stuck on top, if you really say, what are the actual 0th order moduli that solve my equations of motion, how do I parameterize those? So you can vary the moduli, the so-called moduli, such that these equations are not satisfied. Clearly, there has to be some way to describe that. And in 10 dimensions, it's pretty easy to see where this comes from. If you start toggling moduli such that you don't satisfy these equations, supersymmetry is broken at a very high scale, the compactification scale, and that means new contributions to the potential. So starting in 10 dimensions, you can take a piece of your 10D Lagrangian, where F1 and F2 here are my two E8 factors, where you have the Bianchi identity, and you can start rewriting pieces of the Lagrangian to pull out stuff that you're interested in. So just rewriting things in 10 dimensions, you can pull out pieces, positive semi-definite pieces of the 10D Lagrangian that have the following form. These look like the square of the guys that appear in these equations of motion. Why did I bother doing this? Well, these guys depend on no four-dimensional derivatives, so they're clearly part of the scalar potential in 4 dimensions. And as you can see, if you satisfy your equations of motion, these suckers all vanish. If you don't, you're going to be generating some new positive semi-definite terms. If you could do the integration and dimensionally reduce this, you would know exactly what this potential looks like. The problem is that these are a huge mess. You do not know Calabi-Yau metrics except numerically. Likewise, you do not know the connections on the vector bundles satisfying these equations in basically any examples. So you need a set of tricks to say, what is this potential? How do I actually write down the D-term and F-term constraints that I get from this, and how do I use them to my advantage and really determine what the moduli are and whether I can choose gauge bundles so that I have very few of them. Okay, so let's look just briefly at one of these. The first half of these equations is a contraction of the 1-1 part of the field strength with the Calabi-Yau Ricci flat metric. In general, solving these, as I said, you don't know G, so even solving for what the constraints on F are is a pain in the butt. This is a set of wickedly complicated PDEs that you basically have no hope of solving. Happily, you can transform a problem in differential geometry into one in algebraic geometry. This is helped by the so-called Donaldson-Uhlenbeck-Yau theorem, which says that this equations and the holomorphic component, the two not vanishing piece, these are one-to-one with a property in algebraic geometry, which is known as polystability. So polystability, what is that? The claim is that for each polystable bundle, there is a solution if and only if, a bundle is polystable if and only if it satisfies the Hermitian-Yang-Mills equations. What is polystability? This is defined in terms of an integer, moduli-dependent integer known as the, not integer, but moduli-dependent quantity known as the slope of a vector bundle. This is just a contraction of the first Chern class of that vector bundle, which is essentially the trace of its curvature, wedged together with two Kähler forms, so I can write these as Kähler forms in a basis of H11. A bundle is called stable if, for every subsheaf, we'll come back to what the heck that means in a second, if every subsheaf inside the bundle with rank strictly less than that of the bundle satisfies some sort of graded quality for the bundle. You need all the substructure to have a number associated with it, this number, which is less than that of your bundle. Bundle is called polystable if it can be written as a direct sum of stable things, all with the same number, the same slope associated to them. This, you'll forgive me, this is a bit dense, so why am I bothering telling you all this math? We're going to see this appear in the effective field theory in just a second. Just to point out, you've now transformed this problem into algebraic geometry. In principle, it's a lot easier. In practice, you still have conservation of misery. It's tough to find subsheaves and understand the full substructure of this bundle from an algebraic point of view. So, but let's suppose that you can do that for a second and see what it buys you. The reason that this is a nice thing to pay attention to, you know that you have a solution to these guys up here, which are showing up in your scalar potential, if and only if you have a relationship between all possible subsheaves of your bundle and your bundle. So imagine that you have a bundle that could be destabilized somewhere in Kähler moduli space. So it could fail this condition. On a line, generally a hyperplane in Kähler moduli space, this subsheaf is going to become important. You can describe the bundle itself in terms of all possible subsheaves as an extension. If you've never seen a short exact sequence like this before, the only thing to think about is that the guy in the middle, this is the bundle that you're interested in, can be basically written as a direct sum of the guys on the end, non-trivially twisted together over the base. So this is almost a direct sum, but not quite. You can parameterize mathematically the space of such objects in terms of extension classes, and the origin of this extension group is just the direct sum, the thing that you almost have everywhere. On the line where the slope vanishes, in order for SUSY to exist, you need the bundle to decompose exactly as this direct sum. Okay, why did I do all this? There is a point in moduli space, if you have a bundle that becomes unstable somewhere, there is a point in moduli space where this guy that's getting all the action, the subsheaf that is causing you to fail to satisfy your equations of motion, it becomes important, and the bundle can actually be broken down into the possibly destabilizing subsheaf and everything else, the quotient. This means, at that point in moduli space, that the structure group of the bundle becomes reducible. For example, you can have an SUN bundle that breaks into S of UN N1, N2, where these add up to N. This would be something of this type. In terms of a Lie algebra, this is the same as SUN N1, SUN2, and a U1 factor. The point is that with inside E8, that U1 is self-commuting. So as soon as the bundle structure group becomes reducible, you're going to generate new factors in your visible four-dimensional theory. This means that the visible gauge group includes new, potentially anomalous, I'll say what I mean by this in the Green-Schwarz sentence in just a second, U1 gauge fields in the visible 4D theory. Also, all the moduli in the problem can potentially become charged under these new U1s. So again, why am I tediously going through this process? Because I need a way to describe this in effective theory. And it turns out that this rather obscure mathematics of stability, subsheaves, and Hermitian-Yang-Mills equations boils down to D-term conditions, as you might expect in the effective theory. And if you understand something about the geometry of this background, you understand very explicitly what those D-terms look like. So this description was first worked out, the idea that you could break down bundles in this way and describe how fields in the 4D theory become charged under a U1 when a bundle goes unstable was first written down by Eric Sharp. And with various collaborators, we worked on how to do this in Calabi threefolds and how to explicitly work out what the D-term structure is. So to get to the punchline, in general, this half of the Hermitian-Yang-Mills equations gives you constraints, D-term constraints in your effective theory, that constrain the Kähler moduli. So the punchline is that these self-commuting U1s that appear when a bundle becomes potentially unstable are Green-Schwarz anomalous U1s. This means that the axions of, for example, the Kähler moduli transform by shift symmetries under those U1s. And this will lead to D-term parameters in the 4D n equals 1 theory that contain moduli-dependent Fi terms. So schematically, you have a U1 D-term that looks like some Fi term plus some contribution from charged matter. These are going to be bundle moduli that are charged under this anomalous U1. Importantly, quite a lot is known and has been studied in the literature about the structure of these Fi terms, and they have a very beautiful structure that links back to the geometry. So the structure of the tree-level Fi term is exactly just this number mu, which quantized how good this, so how safe this subsheaf was from the stability point of view, the guy that appeared in the definition of stability. And as we saw from stability, the sign of that of this term, whether or not this was less than that of your bundle. So if I have an SUN bundle, for example, if this side is 0, I need all possible subsheaves to be negative. This is just saying that you need a solution basically to this D-term equation. So whether this guy is positive or negative tells you, depending on the sign of your charged matter, whether you can satisfy a D-term in vacuum. So stability is just a D-term. There's a nice one-loop correction to this that was worked out by Timo Rapelmanhagen and Gabi Honecker, which involves the axiodilaton as well, which is also charged under these U1s. If no bundle moduli exist, in general, an Fi term equals 0 is going to fix a linear combination of complex structure in the dilaton. The one-loop correction, this may look like you're deforming away from the notion of stability. In a heterotic M-theory picture and with proper field redefinitions, you can show that this is actually still stability on the heterotic fixed plane, but still incorporates warping and or the dilaton. So punchline, I said this, D-term constraints arising from stability generally constrain some of the Kähler moduli in the dilaton. The overall volume will never be affected. This always drops out of the D-term constraint. And this will give you useful constraints from the gauge fields when H11 is not too big. So depending, obviously your bundle has to fit inside of E8, so it is maximally something like rank 8. If you have 100 Kähler moduli, this is not going to stabilize all of them, but it's some nice constraints that we're going to worry about. So let's look at the complex structure, and then we'll take it from there. So we have D terms arising from half of the Hermitian-Yang-Mills equations. It will not surprise you to realize that the other half of the Hermitian-Yang-Mills equations from the bundle are going to lead to F terms in the effective theory. But let's see briefly what that looks like. So that's this other half of the Hermitian-Yang-Mills equations are these guys, which lead to these pieces in 10 dimensions. In 4 dimensions, you have an alternate description of the same structure, again, from the notion of three-form fluxes. Because the three-form flux is in general built not just from two-form contributions, but also from guys built out of the gauge bundle. So here, omega-3, these are your Chern-Simons terms, which are built out of the gauge bundle, and this Lorentz contribution from the spin connection. You can see that, in general, holomorphic constraints from the gauge bundle can also give you a Gukov-Vafa-Witten type superpotential. Again, the issue is how do you expressly compute it? So this is very similar to what Roberto set up in the complex structure stabilization in type 2 due to fluxes, and he talked about rotating 3-0, 2-1, 1-2 pieces under changes of complex structure. The real issue for where moduli stabilization is coming from is that I have a 2-0 part of my 2-0 or 0-2 part of my field strength, which starts out being 0. I'm going to change the definition of the complex structure of the base. I'm going to change what I mean by barred and unbarred coordinates. And then I can ask, if a bundle started out holomorphic, must it stay holomorphic for any variation of the complex structure in H21? Just like in type 2 with fluxes, the answer is no. You can see this explicitly by writing projection operators. You can consider what happens for the complex structure tensor to this type of equation under a fluctuation of what you mean by complex coordinates. And you get a simple to first order equation which just has 2 pieces. You can rotate the safe 1-1 part of your field strength into the 0-2 part at first order, and you can consider fluctuations of a connection which are not holomorphic, i.e. which do not satisfy F02 being 0. So you have 2 pieces of this type. The question is whether they balance. So for each change in the complex structure, can you find a change in connection which compensates? And in general, the answer is no. So we would have naively said before this analysis that the moduli of the heterotic theory were the complex structure plus bundle moduli coming from each E8 factor, but it's not that simple. So the physics idea is, rather than geometric flux as Roberto described, can we use almost exactly the same tricks using gauge flux? So how much moduli stabilization can we get out of this holomorphic condition? So we want to use this to essentially replace phase 1 of KKLT, and we need this to be a general/computable formalism. The math question is, how do I do that? So given a Calabi-Yau, how do I engineer bundles that are holomorphic, for example, at special loci, subloci, and complex structure moduli space, ideally isolated points? So I'd like to stabilize everything, if I could, with this mechanism. To do that, I'm going to go through this quickly, but mathematically, it turns out that there's a very beautiful deformation theory to help you address exactly this. So just to emphasize, there are 3 different deformation spaces that were used somewhat incorrectly in heterotic literature up until recently. What you normally talk about as the complex structure moduli space is the deformation space of the Calabi-Yau as a complex manifold. So these are deformations of the base manifold itself. You can also talk about what I introduced as the bundle moduli. These are deformations of a holomorphic vector bundle, importantly, holding the base fixed. So freezing the complex structure moduli of the base and varying the fibers above it. Neither of these guys are what actually corresponds to flat directions in your equations of motion, or your potential. What really corresponds to those flat directions is a simultaneous deformation space, which allows you to vary a fiber and a base simultaneously. Simultaneous deformations are not measured by either complex structure of the base or what I called the bundle moduli, but a different cohomology group altogether, something called H1Q, where Q is built as, again, one of these short exact sequence which non-trivially combines the endomorphisms of the bundle, which describe the fiber deformations, and the holomorphic tangent bundle, which describes fluctuations of the base. So there is a different cohomology theory that you care about. You can mathematically define exactly what this is, and just like you said, forget field theory for a second and just mathematically, at the start of the day you had some geometry, you computed H21 and you said this is my background. In principle, this is now a background geometry with a bundle and a space. The correct object that you should be computing to know where you start is H1Q. Turns out that H1Q is smaller in dimension than just the direct sum of these 2 pieces, generically. It can be written as 2 pieces. One is the vector bundle moduli that to this order appear unscathed. To higher order, they can be lifted, and I'll come back to that in a second. Plus something that I've written here as Kerr alpha, where alpha is a non-trivial map between H1Tx and H2 of the endomorphisms of V. These are all the unlifted complex structure moduli of the base. These are the actual deformations that you care about for the moduli of a heterotic theory. So enough math. Let's do this in physics now, because this is going to be easier. So an easy way to build bundles that do what you want and to actually understand what's going on in the field theory is to understand what this holomorphy, how this appears as structural complex structure dependence in the bundle. You want to choose a bundle which can only be built, whatever that means, for special values of the complex structure. Now, if you're a mathematician, depending on your favorite way of building bundles, and there's a whole bunch of them, for any of these, you can see that all of them manifestly have some dependence on complex structure. So the trick is, pick your favorite simple way of building bundles, understand just from the start how building those guys depends on complex structure, and then compare that to this Atiyah deformation story that we just saw. I should have said, just numerology, or excuse me, not numerology, terminology. This guy, H1Q, this deformation theory in simultaneous deformation space was worked out by Atiyah in the 1950s. Okay, so simple example. Let me consider the simplest bundle that I know how to build that's non-trivial, an SU2 bundle which is almost a direct sum of two U1s, two line bundles. And let me consider this as a background of my theory. If I plug in an SU2 bundle inside of E8, I'm going to break down to E7 in 4 dimensions. I chose one particular example here on some background geometry. Why did I choose this one? Well, in order to build this bundle, I need a non-trivial extension class, which allows me to define a stable connection on this guy. And generically, for this line bundle and this manifold, this vanishes. So this bundle, as I want to write it down on this background, does not exist for generic complex structure. Okay, why is that interesting to me? Because the key ingredient that I'm using to build bundles can actually jump at higher dimensional loci in complex structure moduli space, and in fact, in a very simple and computable way. So as I start toggling complex structure, I can see that the necessary building blocks for my bundle pop into existence at certain points in complex structure. So finally, this allows me to give you a field theory description of this rather long-winded bit of mathematics. The Atiyah calculation, if you just do this for this bundle, shows that the bundle obstructs complex structure and you can calculate it, which is really useful. But how do I visualize this in effective field theory? In general, I should give you a little caveat here. In general, just like you can't necessarily, backing up, just like you can't necessarily extract the dimension of H21 from effective field theory, you don't necessarily expect to describe this moduli fixing due to bundles in the effective field theory itself. It's part of the background. It's just the geometry that you're specifying. However, at special points in the moduli space, it can be the case that you have extra light states and you can actually describe this lifting explicitly and determine the F terms that are really obstructing moduli. So in this case, this corresponds to near the split locus. You have an extra U1 charge at this point and bundle moduli that are charged under it. The building blocks that I talked about here are now just two charged fields, C plus and C minus. When they exist in the theory, I can build a bundle. When they don't, I can't. These are E7 singlets. E7 singlets are only in the spectrum of this example. And the point is that cohomologically, these groups jump together as I vary the complex structure. Field theoretically, that just corresponds to a mass term. So I have states in my theory that are E7 singlets charged under some U1, C plus and C minus. If these guys are massless in the theory, I can build a bundle. If they're massless in the theory, I can build a bundle. If they get a mass, they get lifted out of the theory, I can't build the bundle. So what does that look like in terms of an F-term obstruction? If this is my superpotential, I have some mass term which has a complex structure-dependent prefactor. I can choose a vacuum to satisfy a D term such that I give a vev to one of these charged scalars. In order to satisfy this in vacuum, I have a series of F-term constraints. There's one in particular, this guy in the middle, that's going to be of interest to me, which is the derivative of the superpotential with one of these building block ingredient fields. This guy gets a vev in vacuum. I can only satisfy this F term if the polynomial prefactor, which depends on the complex structure, vanishes in vacuum. So there's some constraint on the complex structure. This will give me a supersymmetric Minkowski vacuum. In fluctuation, I can see what happens in the effective theory to my complex structure moduli. For an F term of this type, in general, I'm going to generate a mass for what I've written here as delta Z perpendicular. These are the guys perpendicular to the locus where lambda equals 0. So you can work this out mathematically. You can do an Atiyah deformation problem, and you can see for the background geometry that I gave you, what does a very simple bundle like this do to the complex structure? And in this example, it fixes 64 out of 68 complex structure moduli for this background. You can do it in terms of field theory, in terms of the Gukov-Afawitten superpotential, or in terms of the Atiyah deformation in mathematics, and you get the same answer in any of these cases. Just an interesting aside, the reason I set this up, this type of F-term obstruction, you have to be a little bit careful about equation counting. So if you're saying I want to fix moduli with an effect of this type, you can count the number of F-terms that you have in your theory. It is exceedingly easy, through the mechanism that I wrote down, basically depending on how many bundle moduli you have, to generate a bunch of F-terms. And you say, if I just wanted to do this, say, at the level of GKP, I want to count the number of F-terms versus the number of complex structure moduli. I can saturate that immediately. In practice, there are weird redundancies all over this, and in general, you do not do as well as the equation counting would indicate. So again, Roberto mentioned this. If you really want to stabilize complex structure using flux or this mechanism, it really is important that you actually compute this, because just equation counting generally is misleading, in my experience. Okay.
This part which is not the right. Which order is it? Is it stabilized? Is it a Planck scale or? What?
So this is a good question. So I went to in general, this is at the compactification scale. So these moduli are very heavy everywhere in moduli space. In this particular example, I chose to pick a point in moduli space where this is very light. And if I stay in perturbative field theory next to that point, then this is a scale I can include in my theory, and you have to actually minimize it and work out the full potential, but this is some lower scale of moduli stabilization.
And the VEV? Sorry, I meant the VEV. The C plus.
The C plus VEV?
Yes.
Likewise, at this point in moduli space, it can be reasonable sized. I mean, you're not at the compactification scale. But in general, these are just not ever moduli of your theory. You shouldn't have talked about them. In general, these guys are way heavy. So for the main analysis would be you do the Atiyah computation. That's the thing you can trust everywhere. That's your background. And you don't try and do this in effective theory. But just to illustrate, yeah, you can think of this as F-terms in the same way.
D terms as the number of F terms? Or
no, actually you can get interesting, so you in general need multiple D terms. You can get, so the way that these different D terms talk to each other can give you more constraints than just, again, counting equations there. But it's a good question. For this, yes.
Otherwise the Z are not fixed.
But there's an index
We
here.
can talk about it in the discussion. I mean, there are higher order corrections that can fix the C's as well, but perhaps we can...
Yes, right.
Yeah,
I agree with that. Yeah.
One thing that you might say is at the moment, I haven't stabilized the C's. So I needed a bunch of C's to stabilize the complex structure, and I haven't addressed those yet. I have several things to say about that in the next 5 minutes if I get to it. Here I just point out there is an index, so I have a lot of F terms from one D term. Okay. So really quick comment on some global questions of moduli space. The analysis I just gave you, both mathematically and field theoretically, was a local one. I started with a deformation problem, so physically I'm starting at a point and considering the effective theory around some minimum. Mathematically, I'm considering infinitesimal deformations, again, around some chosen geometry. The big limitation, suppose that you were lucky and there existed a bundle that stabilized all your complex structure moduli. The sucker's totally rigid, it does exactly what you want. The problem is, how do you find where that was? So you can't do this with an infinitesimal analysis because you needed to know where to start in order to see that it was rigid. So the question is, can you actually do a global moduli space analysis for bundles? Can you scan over all possible bundles in some sense and all possible minima to this potential, not from an infinitesimal point of view, but globally? So can you find from the top down bundles that will do exactly what you want? And some recent progress in this, we figured out nice ways, I won't go into the details of this, but nice ways mathematically to be able to scan over a complete moduli space. And there is amazing and very rich substructure for this. So for the simple bundle that I wrote down, there are in fact 27 disconnected distinct branches to the solution space in complex structure moduli with different numbers of moduli stabilized. And it is possible to scan over all of these. And also we figured out how to actually track this type of data through conifold transitions. So you can do this calculation once and then consider chains of Calabi-Yaus connected by geometric transitions where you have the same information about how the moduli gets stabilized. So I'm happy to talk more about that in the discussion session, but point is we have some sophisticated tools now for actually solving exactly how this moduli stabilization works. So I got 5-10 minutes? Okay. Let me just say a word about another and older type of idea of using gauge bundles to try and stabilize moduli. In the case of non-simply connected Calabi-Yaus, which I haven't discussed so far, these guys are interesting if you want to include Wilson lines, which you frequently do for model building and for breaking gauge groups. There's interesting work by Gukov, Kachuk, Liu, and McAllister, which said perhaps you could generate Gukov-Alpha-Witten superpotentials from things like Wilson lines, fractional Chern-Simons invariants, coming from combinations of terms like this, where the A in here is now flat. Examples were known in 6 dimensions for heterotic orbifolds, where in principle you could get non-trivial Chern-Simons invariants, which are non-vanishing for Wilson lines on lens spaces. The hard part about this is an interesting idea. No Calabi-Yau threefold examples have been computed, and no tools are readily available. So unlike the case that I just described, we don't really know how to decide whether a contribution of this type is 0 or not. We also don't know, in known examples, Wilson lines can generate an omega-3 Yang-Mills. However, I don't have the full potential up here, but you have 2 different pieces, omega-3 Lorentz, omega-3 Yang-Mills, and B-field contributions here. So the question is, does this get canceled? Can you actually use this the way you want? There's also issues about sizes. These guys commented that you could in principle try and get a small flux superpotential where you have some integer divided by the order of a discrete group that went into this quotient to build a non-simply connected manifold. Again, there's a question about whether this is large enough, but it would be interesting to explore further. So question mark, can you get something cool from Wilson lines? At present, we don't really have the technological control to describe this. And finally, just before I put everything together, non-perturbative effects. The ingredients are the same as Roberto has mentioned in detail in his talk. In general, you have worldsheet membrane type instantons, Gaugino condensation terms. And in general, the prefactors of these A alpha and B betas, these guys depend on both the bundle moduli and the complex structure moduli of your theory. There is, in principle, a very rich structure here. As you add in these non-perturbative effects, you can stabilize all sorts of things, not just in the exponentials, but also through the prefactors. Unfortunately, they're very hard to compute, and really nailing down all the non-perturbative effects to the level of detail that you need has only been done in very few examples. So it is possible that you could try to do interesting tricks, for example, racetracks with non-perturbative effects for small numbers of moduli. But anything in your moduli stabilization scenario that depends sensitively on these guys is going to be tricky unless you can explicitly calculate it. There are issues that you have to pay attention to. Do these instanton contributions sum up to 0? In some geometries, it's known that they do. In some geometries, they do not. So again, you have to actually do the calculation to know whether you have the tools that you need. Other less well understood ingredients, just to mention it for the sake of thoroughness in potentials, you could consider antibranes in heterotic, much like in KKLT. This has been studied systematically by Gray, Lucas, and Overett. Thus far, they wanted to see if you could get you could wrap antibrane on some small cycle and have a controllable supersymmetry breaking at some appropriate scale. Thus far, this has been unsuccessful. Their work showed that this wasn't really turning out very well. No vacua were found and an unphysical scale of supersymmetry breaking. But perhaps in the future you could do something with that. You could also consider alpha prime corrections to the Kähler potential. Some work has been done on this, although this is not at present. So the work that was done has issues with it that I think are pretty universally agreed upon, and this hasn't been done, again, to the level or sophistication as in type 2 that it needs to be. You could also try, for moduli stabilization, explicitly computing matter field Kähler potentials, and there's some numerical tools that may be applicable for that, but at present are too slow. So let's try, in the last 5 minutes, to put everything together and just see what types of things you could do. Hopefully the tools that I set up so far, in principle, you could do things like you do in type 2. You want to do a multi-step process in which you stabilize different moduli with different effects. So the first natural stage would be to try and get rid of complex structure moduli via, for example, pointwise holomorphic vector bundles in a hidden sector. These would be F terms. This is relatively easy to accomplish, and we're developing much more sophisticated tools for seeing exactly how those moduli are stabilized, which I should say in heterotic, all your physical Yukawa couplings are functions of those complex structure moduli. So if you want to do model building and really understand the mass of the electron at the end of the day, you need to be able to explicitly understand where those moduli are stabilized. You could try and use D terms to constrain Kähler moduli and dilaton-dependent Fi terms. So, for example, have a hidden sector which is reducible, which leads to these Green-Schwarz anomalous U1s. If there's no charged matter under the U1 symmetries, you could stabilize all but one linear combination of T or S in principle. May be advantageous to do less. The resulting moduli space at the end of this perturbative story now would be supersymmetric in Minkowski. At that point, you could try and add non-perturbative effects to both break supersymmetry and stabilize the remaining moduli. There are some issues that you have to be careful of at this point, though. In using the ingredients as I set them up, The U1D terms that I wanted to use to constrain Kähler moduli arise from axionic shift symmetries, and any non-perturbative effects we introduce have to be compatible with those that U1 invariance. This tends to create tension between the moduli stabilized in stage 2 and what non-perturbative effects can be introduced in stage 3, i.e. what exponentials here are really compatible with those U1 symmetries. So in general, if you over-constrain yourself with D terms, you run out of non-perturbative effects to use.
Where is stabilizing the vector bundle moduli?
So as I just set this up, there are two possibilities. So as I described this guy, to first order, this stabilizes only the complex structure. If you consider this calculation to higher order, which I didn't have time to do, you can lift bundle moduli that way. I also, if I had time for it, have one other slide on how you would do this, basically involving. Okay, let me not get to that just yet. One other thing. So higher order in this guy, and these prefactors are functions of the bundle moduli as well. In the case of gaugino condensation, you don't really understand how to compute that. At least I don't. This has been computed explicitly in some instanton examples. Okay. I agree that this is dodgy. So you don't want, I mean, if you're doing the whole thing here, this is not going to be the greatest. Okay, so you would want to get bundle moduli as some combination of stage 1 and stage 3. In general, you have some sort of tension, so again, you have to work out what all these pieces are.
Why do you forbid charged instantons? I mean, like in 2B, also the closed string fields get a U1 charge, but then you just get open string modes, or like here bundle moduli that cancel the charge that appear in the prefactor.
Yeah, that's possible.
Yep.
No reason to forbid.
Absolutely, you just have to work out what, well, it depends on an example. So I am not claiming that these are totally forbidden. It's just there is some non-trivial U1 invariance is the only point I'm trying to make. You're absolutely right. You can have bundle moduli prefactors that are charged, work it out, figure out what's allowed. In general, it won't be everything, and then you have to see what's left.
But you must make sure that no field in front is one that you want to keep at 0 vet, right?
Agreed.
It could be a standard model field. That's the problem.
Well, these, okay. So you're saying, could I have charged matter that appears as these prefactors? If I'm doing this in the hidden sector, then no. But yes, agreed, there's a bunch of stuff. So this is just a set of ingredients at the moment. In principle, you could try and put all these together, try and stabilize all geometric moduli. The bundle moduli are clearly the most problematic in this in a controlled region of parameter space. And I think I'm almost out of time, so let me just say a little bit more about the bundle moduli and the supersymmetry lifting. I should say that perturbatively, we have demonstrated that you can get a very long way just with perturbative effects. Once you're relying heavily on non-perturbative effects, clearly life gets a lot harder. Just to say a couple of other interesting directions. So one thing you can consider is to say, instead of a Calabi-Yau background, suppose that I tried to use the same tools in the Strominger system. So can I use this bundle flux in, for example, a Strominger background, where now I have non-trivial H flux as well to try and stabilize moduli? In recent work with James Gray and Eric Sharp, we did the same fluctuation analysis for holomorphic bundles in the context of non-Kähler Strominger system solutions, where the background manifold was still complex and satisfied the DD-bar lemma. In this case, we found a very analogous story to the Atiyah deformation story. In this case, it turns out that it's not about holomorphic deformations of the total space of a bundle, but, excuse me, not about holomorphic complex deformations, but it turns into something that resembles generalized complex structures on the total space of a bundle. You can work out just brute force what to first order the fluctuations from your equations of motion actually give you. And it gives you some interesting structure. I'm not going to get into this today. The point is that all your bundle moduli in principle can be lifted. The reason that you might care about this is you know that to higher order in alpha prime you're deforming away from a Calabi-Yau background. So if you keep track of the alpha prime expansion even in the Calabi-Yau case, you expect that these are giving you contributions that lift your bundle moduli that may in fact be computable. So happy to talk about that more in discussion. Other examples, flux, other examples of interesting and recent progress. Various flux and Calabi-Yau vacua are possible with domain walls. Interesting work there from Lucas and Matti, who showed that you can in fact have non-trivial harmonic flux and Calabi-Yaus possible to all orders, excuse me, possible to the order that you're interested in if you give up Minkowski, if you have domain walls. There's also model building and moduli stabilization on more general SU3 structure spaces for which progress has been made. It would be nice to be able to put this together and understand flux as well as the various effects that I've described today in these contexts. But these theories are still not fully understood, but exciting developments are underway. So let me conclude, because I've run way over. What I wanted to set out for you today was that we have a collection of tools. As I said, this is not as developed as it is in the type 2 setting. We do not have a complete scenario like large volume, but we have a far better shot at it than we had until very recently. We have abundant, explicit, and very computable tools. So the geometric Neveu-Schwarz and gauge flux, D terms and non-perturbative effects. So the F term lifting due to gauge flux in particular is a nice tool. Recent progress has been made in combining these for straightforward and reasonably generic moduli stabilization in Calabi-Yau vacua. The real thing that I didn't have a chance to get to, and I hope we can discuss more in the discussion session, is you want to put these together to find completely stable supersymmetry breaking vacua. In my personal opinion, I feel like the moduli stabilization is coming together in a fairly generic and very computable way in terms of being able to stabilize moduli in ADS or Minkowski vacua. Once you talk about mechanisms for supersymmetry breaking, I feel like we're still missing something compelling, honestly. There's a big question mark about how you put these together and how you're really going to find stable DS SUSY breaking vacua. As I mentioned before, gravity mediation is probably the way forward, so understanding exactly how these hidden sectors are going to work and what scales you get is important. Also, just to say again, because this all plays together, as I mentioned at the beginning, model building, moduli stabilization, and supersymmetry breaking all have to be done more or less at once in heterotic theories. One attractive thing is that model building in heterotic theories is reaching a much more sophisticated level, and it's really crucial to be able to combine all these three pieces and put everything together. I'm hopeful that we're making progress in this area, and there's some exciting progress which I didn't really have time to talk about today in non-Kähler compactifications. So I'll stop there.
So thank you very much for both speakers this morning. We'll reconvene at 11:15 with a discussion about